All right, good morning. Oh, how is everyone? Awesome. For the past week plus, I've been watching the slow crawl of some printed circuit boards trying to get out of China. And it's Chinese New Year, so things are extra interesting, and these things keep getting held up for customs checks, and they left Hong Kong about 7 minutes ago, but I don't know where they're going from there. So don't ever watch mail being delivered. It's never very satisfying. All right, any questions? We're going to go ahead and play more with trees, but any questions first? All right, cool. So let's look at insertion into binary search trees. So setup was the following. We have a tree, it looks like, I don't know, it's got stuff on it. So there's a tree, and we want to insert, I don't know, let's insert 27. And so we insert the same way we search. We start from the root, and you know, the root's the way we get a hold of the tree. And 27 is bigger than the root, so move to the right. 27 is bigger than this root, so move to the right. 27 is smaller than this root, so move to the left. 27 is bigger than this root, so move to the right. But there's nothing available to the right. So instead of saying, you know, 27 wasn't found, what we do is we attach 27 to the right. And as long as we do that, we're still going to have a binary search tree. So that's what we want to write some code for, and I'm going to put together some code here, and we'll implement this, and we'll play around with it, and we'll see this business of double pointers that I alluded to yesterday, and so on and so forth. So let's jump in and implement this idea of moving down the tree. So let's write some code. So I'm going to make a T node. It's going to have a data field. It's going to have a left child. It's going to have a right child. All right, and I'm going to make a type def. I got into all kinds of trouble last period doing this, but we'll see if I can do a valid type def. So I'm going to make an uppercase T node, which is just a struct T node. The hope is to not have to type struct T node, struct T node, struct T node again and again and again. And a T node is not a pointer. A T node is actually a node, right? So anytime I want a pointer, I'm going to do a star T node. Yeah, you can type def. Well, I can't use the type def inside here because I wouldn't have defined it yet. All right, so let's write a test main program. So the root of my tree is going to be a pointer to a node. So this is my tree, and I initialize it to null to say there are no nodes. Remember, there's no sentinel nodes with trees, so an empty tree is represented by null. So let's insert stuff into the tree. So let's insert a 10, and insert a 20, and insert a 1, and insert an 11, and insert a 5. So this is just test code, right? I'm not thinking, you know, front-end interface, scanf, all that kind of stuff. I just want to develop my insert function. And I'm going to see what it's doing by running this in GDB. Okay, so this is the other part of this is, you know, GDB practice. Alright, so let's make our insert function, and I'm going to make it void to begin with, and we're going to see what happens. So I'm going to prototype my function, and my insert's going to take a pointer to a T node, that's the root of a tree, and it's going to take a number. And first thing I'm going to do is I'm going to want to insert, I'm going to want to make a node to insert. So if I say insert 27, what should I do? I should create a new node, which looks like a miniature tree. It's going to be a single node with a data value of 27, left and right children null. Yeah, we'll add the return value in a minute, because you're absolutely right. But I want to see what happens if we don't do that, to try to motivate why we do want to do it. So let's make a new node. So my new node is going to be a pointer to a T node. And what should I malloc here? What's the correct argument? Size of T node, perfect. Right? So I don't want a pointer to a T node, because a pointer only allocates 8 bytes. I want a size of this actual node. And this is part of why I typed ft node to be, you know, an actual node instead of a pointer. But mostly I want to know when I'm dealing with a pointer. I want it to be really clear to me while I'm developing my code that root is a pointer and this is not a pointer. Right? So yeah, so everyone's absolutely right. It should be size of T node. And then we want to set the fields of this node. So set the data field equal to our number. So I'm going to set the left and right children to be null, and the data field equal to the number. Let's find where we should insert this into the tree. So I'm going to make a temporary node pointer, and I'm going to initialize it to root. And we're going to use that to move down. It's clearly Typo Tuesday. And I'm just going to do this as a forever loop, because I'm going to basically start navigating down the tree, moving left and right and left until I get to the spot where I want to insert my new node. I'll attach my new node at that point and I'll return. So if the node I want to insert is smaller than the root of the tree that I'm looking at, and remember, as we move temp down this tree, right, as we move it down here, temp is the root of another tree, right? It's no longer the root of the original tree, but it's the root of its own tree, right? If temp is pointing at the 20, well, that's a root. If temp is pointing at the 30, that's the root of this tree. So it's kind of the same logic no matter how far down the tree I've gone. And the logic is, if the number we're trying to insert is smaller than the root of the tree, then we want to add somewhere to the left. So we want to move to the left. Otherwise, we want to add somewhere to the right. All right. Well, what we've got right now is good for moving down the tree. Let's say we want to insert our 27, and this wasn't here, right? We'll start here. 27 is bigger than the root, so temp will become here. 27 is bigger than the root, so temp will be here. 27 is smaller than the root, so temp will be here. 27 is bigger than the root, so temp will change to null. But once that happens and we come back here and we look at temp arrow data, we're going to seg fault. We're not going to worry about equal, but yeah, we could make a rule for if it's equal. But pretty much everything we do in trees, I'm just going to assume that numbers are only in the tree once, just because it saves a lot of special cases. So what we need to do before we move to the left or the right is make sure that there's actually a node there. So the number smaller than the root, we want to add somewhere to the left. If there is no left child, add our new node here. So if the left child is null, we'll just set the left child equal to the new node, and we're done. And same thing down here, if we're moving to the right, before we actually move to the right, let's see if there is a right child, and if there is not, then we'll set the right child equal to our new node. Otherwise, move to the right and continue from there. All right, so here's most of an insert routine. Right, when we run it, we're going to seg fault. So let's run it inside the debugger. And so our main program starts off with setting root equal to null, so we'll go ahead and do that, and we'll look at our root. And it's in the insert routine where the seg fault's going to happen, right? If I just say next, I'm going to throw my seg fault. So let's start over again. And let's set the root equal to null. I want to actually go inside my insert routine and start debugging inside there. So instead of next, what's the command I use? Step. Perfect. So I step. Now I'm inside insert. And it's telling me I called it with two arguments, a root which was 0 and a number which was 10. So I'm going to do malloc. Now I don't want to do step here. If I do step, I'm going to step inside malloc, and now I'm debugging system code, and that's just a big nightmare. At that point, just Control-C out and start over again. But I'm going to do next, so it will come back from malloc. And let's look at new node before I do this. New node is null. So I'm going to call malloc, and now if I print new node is, you know, pointing somewhere. And if I look at what new node is pointing to, it happens to be pointing to a bunch of zeros. That's okay, we haven't really initialized it. Now I'm about to say new node arrow data equals num. Let's do that. And let's set new node left and right equal to null. And now if I look at new node, hey, that's a nice node. That's a node with a data value of 10, left and right children of 0. Alright, I'm going to set temp equal to root. And remember, root is null because our tree is empty, so temp is equal to null. And so what's going to happen right here at line 40? What's going to be the effect of executing that one statement? Temp is null, which means seg fault. Right? And it's going to say, hey, you're trying to access memory location 0 and you can't do that. Right? Temp is 0, print temp arrow data, can't access memory location 0. So that's where our seg fault's coming from. And why is it happening? Because our root is null and we can't move down a tree if root is null. This works great as long as root is actually pointing to a node, but in the one particular case where our tree is empty and root is just null, this doesn't work. So it's an edge case. It's an edge case we avoided with linked lists by having a sentinel node, but we don't have sentinels here. So we're going to have to deal with the edge case ourselves, but it's not that hard. So is the tree empty? Yes, this is an edge case. So if the tree is empty, what do we want? We want to turn the tree into a something containing just a single node, which was this new node that we created. So we'll set root equal to new node, and we're done. Alright, so let's run through this again. We start off with root equal to null. We step into our insert code. We create a new node. We set the data value to num. We set the left and right children to null. We check to see if the root is null. And it is, so we set root equal to new node. Let's take a look at root. Root is not null anymore. It's pointing somewhere. Where is it pointing? It's pointing to our node containing a 10. So now we have done something. We've made a little tree containing a 10. So we'll go ahead and return to our main program. And now we're going to insert a 30. And we're going to come in here. Yeah, 0 is equivalent to null. Oh, we're going to insert a 1. Okay, so I'll step into my insert routine. I'll create a new node, set the data value to num, set the left and right to null. So if I look at new node, that's our node with a 1 in it. That's all great. Now we're about to say if root is null, and guess what? It thinks root is null. Why? Because root is null. So we'll set root equal to new node. Okay, root's pointing to a -1. Let's return. Now we're about to insert an 11 into our tree. and we're going to allocate space for a new node, and we're going to say if root is null, and guess what? Root is null. So what's going on here? I'm clearly setting root to something different from null, but when I return to my main program, root is still null. So what's the problem? Why isn't this working? You can print your code in GDB, yeah. You can say list, and it'll show you your source code listing. So it saved the node that was allocated in dynamic memory, so that's still around. And I could go back in with that actual address and look at stuff, right? Right, and that's still got my data value of 11. But when I come back in here, root is still null. So why isn't root being changed? Three-word answer. Yeah, pass by value. And what you said a moment ago, right? We need to return it, basically. When we pass root, even though root is a pointer to a T node, right? We pass the value of root. So root starts off its existence as null. When we say insert root 10, what we're really saying is insert 0, 10. Now inside insert, this variable root is set equal to null. And down here, this variable root is changed to the address of our new node. But that's changing this variable. And this variable and that variable, nothing to do with each other. They happen to have the same name, but they are completely different variables. And changing this does not change that. Right? Because it's passed by value. Passed by value, you hear this a lot. All it means is, you know, whatever the value of root is, we could have just said insert parentheses, that number, comma, you know, the rest of the arguments. And so this is a local variable, which is set equal to, you know, null in this case. And here we change the value of that local variable. When we come back here, this version of root is this variable up here. And it definitely has not changed value. So there's two ways we can deal with this. One way is to pass the address of root, just like with scanf. We pass the address of I so that scanf can change the value of I. So we could pass the address of root, but if we do that, then we need to declare this as a t-node star star, right? A pointer to a t-node star. And then everywhere that we use t-node, we use star t-node, and down here we would, you know, star t-node equals new node. And it gets really bizarre looking, right? And it doesn't feel right, and it's actually not the best way to do this. We have the option of returning a value from insert. Right now we just set it to void. Since we've only got to deal with this one variable, root, that we want to change the value of, what we're going to do is we're going to change insert to return a pointer to a t-node. And so we're going to change our code as follows. We're going to set insert to return a t-node pointer. And then everywhere that we call insert, we're going to set root equal to the return value. Now inside insert, it's going to change the value of root maybe. We're going to have insert return the new root. So we need to make a little bit of change here. We'll tell it that insert is a pointer to a t-node. and we'll just return root as the function value. When we move down and we find a place to attach our node, we're going to return the root there, and if we move to the right, we'll return the root there. Now it's perhaps a little peculiar that the only time root ever changes is right here. So the root that we return here is going to be exactly the same root that we were called with. So this is kind of a no-op, right? Once we have something in the tree, whatever we pass to insert, that's going to be what we get back. But that's okay, we're just setting root equal to root again and again. That's not a problem. It's worth doing it like this so that we have kind of a uniform appearance to our code. Alright, so recap, right? Insert is going to return the root of the tree, which in the case where we called insert with an empty tree, it's going to return a single node, right? A tree that looks like that. But once we have stuff in the tree, we're going to call insert with the root of an existing tree. It's just going to return back the root that we passed it. I think you could do insert, arrow, insert, insert. Yeah, I think you can. That would be interesting to do because you're very dependent on the order in which those insert calls are made. That would be interesting. But yeah, you should be able to do that. Alright, so let's compile this and run it. You wouldn't believe how many compile errors I had this morning when I was doing this in the A section. I mean, I had a 20-line program and I was getting like 50 errors out of it. So we're lucky right now. We could use a pointer to a pointer, and that will work, but it's going to make your code really complicated, and it's absolutely not the way we want to do it. And it will actually like break some things down the road. But technically that would work, and that's how we would do this normally. If we wanted to change the value of something we passed, we would just pass a pointer to it. So yeah, that's exactly right. But we're not going to do that here. We're going to use the return values. Alright, so let's run through this. We have a root which is null. We're going to call our insert function. Let's step into the insert code. We're going to create a new node, which we call new node. So there's our new node. It's a 10. And let me modify our picture. So our root is null to begin with. Alright, we're going to say if root equals null, and in this case that is true. So we're going to set root equal to new node. So root's pointing somewhere. Where does it point? It points to something with a 10. And now we're going to return root. So we return back to our main program, and now in our main program, if we print root, it's pointing to, you know, that location that has a 10 node. If we print the thing root points to, it's got a 10. So now root looks like a 10. Alright, so we got a tree with one node. Let's go ahead and call insert 30. So we'll step into our insert function. We'll allocate space for a new node. New node is equal to 30. We're going to say if root equals null. Well, root is not null. Root is exactly the same thing that it was the last time through here. So we'll skip over this if root equals null business. And now we'll say set temp equal to root. So temp's got the same value as root. So here's temp. And now we're going to say if our number is less than temp data. Well, our number is 30. So if our number was less than temp data, we would want to go somewhere to the left. So we're going to skip over all of this code, and we're going to come down here to this else statement. So let's next that. And so now we're executing this code, which said check to see if temp right is null. Well, if I look at temp right, it's null, right? Because remember, temp is this 10 node. So our code says if temp right is null, what should we do? Set temp right equal to new node. So let's execute that, and now let's look at temp right again, and it's not null. It's the address of some new node. And if I look at temp, right, it's got our data value of 10. The left child is null. The right child is not null. And if I look at the thing that temp right points to, that's our node with the 30. So let's return that root back to our main program, and let's see what's happened. So here's our root. Our root has a value of 10. The left child is empty, right? So it's a 10 with nothing on the left. But the right child is not empty, so there's something hanging here. So if I look at what root right points to, it's a node with a 30, and that 30 has no children. So this is pointing to a 30 and no children. And when we draw trees, if there's no children, we just leave it blank. We don't usually draw a line and say null. We will one day. Alright, we're about to call insert 1, so let's go ahead and do that. Let's step into our insert routine. Let's make our new node. Root is not null, so we set temp equal to root, and we're going to compare our number 1 to the root node's data. And 1 is less than the root node data, so we're going to want to go to the left. So we check to see if temp left is null, and it will be because that's the root node. So we set temp left equal to our new node containing a 1. We return the root, we come back into our main program. Let's look at root. Let's look at what root points to. It's a 10 node, but now there's something on the left as well as on the right. So we got something hanging here. And if we look at what root points to on the left, it's a node containing a 1. So now we got a cool looking tree. It's got like 2 children, 3 nodes, and it's a binary search tree. So we can insert an 11 and we can insert a 5, and we're done with our code here. Let's take a look at root now. So root hasn't changed from the beginning when we first assigned it. It's a 10 with stuff on the left and the right. If we look at the left subtree, that's a node of 1 with something to the right. So we have something here. And what is that thing? Well, we can print root left, right. As we can see, that's a node containing 5. And this arrow notation is really working for us now, right? So this part is saying, okay, I've got this variable root. It's a pointer. Look at what it points to. Give me the field called left. Well, that's the address of the left node. This arrow says, hey, this thing so far is a pointer. Take the thing it points to. Give me the field called right. Well, that is a pointer to a node on the right. It's a pointer to this node right here. And this star in the front says, give me the thing that all of this points to. So show me the contents of that node, and that's how we can see it's a node containing a data field of 5 and left and right children that are null. So we got a 5 sitting right here. And if we print root arrow right, that's our 30, and it has a child to the left, nothing to the right. And if we look to the left, that's a node with an 11. So our root right points to a 30, and 30 left points to a node containing 11. And so root is a tree here. And it's a binary search tree. Everything over here is smaller than 10, everything here is bigger than 10. Everything over here is smaller than 30, everything over here is bigger than 1. Alright, instead of double pointer, could you pass a reference instead address T-node? Yeah, we could pass the address of T-node, but then in our insert routine it would still be a double pointer. We have to say this is the address of a T-node. Which would be, yeah. Yeah, if we passed address of root, that's the address of a pointer to a T-node. So insert would say that's a pointer to a T-node. All right. Give me your favorite number that's not in the tree already. "24 came in first. So let's insert a 24. So I'm in GDB, I've got my whole memory structure here, and this is where you want to be working, by the way. All right? You can do all of this by just, putting prints in your code and recompiling and rerunning. It's going to be a lot faster if you can actually play these games inside the debugger. And the more practice you get with the debugger, the easier time you're going to have. Because if you have to stop what you're doing and figure out where you were in your code and add some print statements and so on, it's a really long development cycle. Right now, I can look at anything I want in memory. I can break it down and look at this using the debugging information that knows, that the T-node begins with data, followed by left, followed by right. I could also, if I really wanted to, I can just start examining memory directly. And I can look at this and I can figure out what my structure is. But, if you compile with -G, we can do things like, root arrow left, and it knows what we're talking about. We can also trick GDB into running code. So let's do this. Let's print root equals insert root comma 24. I'm asking GDB to print something. What am I asking it to print? The value of root. But I'm also telling it to assign root equal to insert root 24, which is going to force it to call this insert function. So I don't have to go back and change my code. I'm writing C code live while I'm inside GDB. All right. So the root hasn't changed, but in executing that statement, I forced it to call insert. So let's see what root's pointing to. It's still pointing to a 10. And the right child is pointing to a 30, and the 30 has something on the left, and the thing on the left is the 11, but that 11 now has something on the right, and if we look at what's on the right, it's a 24. What did we just do? We just put a 24 right here. Alright, and then second favorite number coming in was a 47. Well, maybe not favorite, but suggestion to insert was a 47. So let's do this again. Let's insert a 47. So there's root. Root arrow right is our 30. And when we did this before and we looked at root arrow right, it had something to the left, but the right child was null. Now, node 30 has something to the left, but also has something to the right. What ended up on the right? That's the number 47. So 47 got added to the right of the 30. In other words, it popped in right here. And 47 has no children. It's a leaf node. All right, so someone said let's do 69, so let's insert 69. And if I look at that 47 node, suddenly I find it's got something to its right. Right up here, 47 was a leaf node, no children. Now 47 has a right child. And if I print the contents of that right child, guess what? That's 69. So that new node got tacked on right here. Right, we're building trees. And we're getting to all of this data from this one variable root. All right. Now, when you write tree code for PA4, this is not how you're going to be doing it. We're going to be doing a very different, much kind of slicker way to insert things into trees. But this is effectively what's happening, right? Start at the root, move down until you get to the insert point, and then tack your new node on. The pointers and return value, all of that stuff, absolutely are confusing, right? And that's part of why we're doing all of this, is to get more familiar with pointers and addresses and the arrows and things like that. And you've got to, there's no shortcut, right? You can find a development environment that will show you all of this, right? That you could say, show me what this tree looks like, and it will just print out a nice picture of a tree, right? That does you no service, though, as far as learning what's going on in the memory of the machine. And you really want to figure out at a conceptual level, right, what this means, what this root arrow right means, and what star root arrow right means, and why we get this, and why star root arrow right is related to this, and so on. And it takes you know, practice and trial and error and big sheets of paper and good music and talking with friends and all kinds of things, right? And I can't give you an algorithm for conceptualizing this, but it comes with time. And when you get to the point where you can hop into a debug session and you can do these kinds of things, right? Data structures no longer an issue, right? It's no worse than trying to find a parking spot. You know how to do it. It might take a really long time, but you know, you've got algorithms down for it. All right, so let that percolate for a while. Well, we all have some kind of algorithm for finding parking spots. Mine's not very good. I find the first spot and I grab it, even if it's a half mile from where I'm going. All right, let's talk about traversal. So we've got a binary tree, and we want to print out the contents of this tree. And it's not like a linked list where we can just start at the root and just follow, you know, from one node to the next to the next. Right off the bat, we've got two choices. We could go to the left or we could go to the right. And if I say, okay, I'm going to start off by going to the left, I need to remember where I was. I need to put some kind of like marker there and say, hey, don't forget, you got to still come here and go to the right. All right, so I'll start off here and I'll go to the left. And now there's a point here, there's another node. Well, there's nothing to the left, but there is something to the right. So I'll go to the right and I'll deal with the 5, and I'll come back here and deal with the 1. Now I come back to the spot I marked, that's the 10, and I can deal with the 10. Now I've got to deal with this tree. So I'm at the 30, I've got two choices. go this way or that way. So I'll put a little marker there, I'll go this way, right? And deal with the 11. And let's say there was another node over here, right, like that. So I'm dealing with the 11, I go over here to a 24, right? Well, I've got to deal with, left and right children here, so I need to remember where I was there. So, I'm going to put some kind of marker right there on the 11, and come over here to the 24, and there's a left child and the right child, and there's the data, and I'm done with that, right? Now I've got to come back to the 11, and once I get back there, I've got to go back to the last place I put a finger down, which was my 30, and now I can start going to the right. Okay, this is maze running. This is what we do when we solve mazes. You get to a point where you could go left or right. Well, you kind of put your finger there and you try going to the left. And you follow the maze and you hit a dead end, so you come back to where your finger was and you try going to the right. And if that hits a dead end, then you shouldn't have been here at all. So you take that finger away and you find where your previous finger was keeping a spot. And if you had gone left there, now you try going right there, and maybe that gets you further, and you get to another decision point, so you put a finger there and you try going left. If that doesn't work, you come back to that finger and you try going right. And if that doesn't work, then we go back to the previous spot. Well, we tried all directions from here. We've got to go back to our earlier spot that we had put, some other marker on, right? So maze running, right? What's the data structure that we're using here? Every time we get to a spot and we've finished visiting all of these nodes, we have to back up to the last spot that we had made a decision from. And if at the last spot we went left, now we have to go right. What's the data structure here? Something from a couple of weeks ago, before we got to trees. Something about running mazes. It's a stack-based structure, right? In other words, a LIFO. The last time that we made a decision, that's the first spot we're going to go back to and make a different decision. So searching through a tree like this in order to visit every node, traversal just means visit every node. Traversing a tree like this is fundamentally a stack-based operation. And that's one way to do tree traversal. We can also traverse a tree using a queue. And that'll give us a very different order in which we visit these nodes. But if the goal is just to visit every node, right, say we just want to print the contents of the tree in no particular order, we can do that a number of ways. But if we want to print the data in order, it turns out there's a really slick way to do that. And so I'll give you a preview of where we're going. We're not going to do this tomorrow, but we'll get to this by the end of the week. Let's say we wanted to print out the data in this tree in order. We start with the root, okay? But before we print this, what we do is we make a subproblem. We say, hey, here's a tree, and we hand this to a friend and say, can you print the data here in order? And they'll say, sure, so 1 and a 5. Okay, you get that list back from your friend, and now you print this node, and now you take the subtree on the right and hand that to another friend and say, hey, can you print this data for me in order? And they say, sure, and they hand you a slip of paper that says, 11, 23, 24, 25, 30, 47, 69. And bingo, we printed all the data in order. The question is, how did your friend print this tree in order? Well, they did something really sneaky. They looked at the left subtree of the root, and they handed that to a friend and said, hey, can you print the contents of this tree for me in order? And their friend said, sure, it's 11, 23, 24, and 25. And then your friend printed the value of the root node, and then your friend took this tree and handed it to someone and said, can you print this data in order? And they said, sure. And then your friend took all of this and handed it back to you. And you printed it after the 10, and bingo, you succeeded in printing the data. Okay, so this is a preview of recursion. Recursion is really just having a friend who will, you know, do a smaller version of your problem and give you a solution, and you can put that into the solution to your problem. All right, we are out of time here. We will play with stack-based traversal tomorrow, and then we will we'll probably look at queue-based traversal, and then we'll look at a few more properties of trees, and then we'll come back and we'll start looking at these this business of traversal a little more carefully. And then we're going to move into recursion. And recursion may not hit until Monday. We'll see how far we get tomorrow and Thursday. All right. Bring questions to class tomorrow on PA3 or on any of the material. And I will see you then. Have a good afternoon. Thanks.